February 10, 1944, the Apennine foothills, north of Cassino, Italy. Morning haze drifts across the valley floor. From the shadow of a ruined farmhouse, 4 men of the 36th Infantry Division move forward along the ridge, their boots sinking into wet soil. Each carries a Springfield rifle wrapped in burlap to dull the reflection. The air smells of cordite and smoke left from the previous night's bombardment. Private First Class Harold Whitman walks last in the line, his rifle held carefully across his chest. 2 days earlier, a mortar burst had thrown him into a wall and split the rifle stock clean through the wrist. The rear sight leaf had twisted from the impact. According to his platoon lieutenant, the weapon was written off as unserviceable. But Whitman refused to hand it in. He spent the night under a ration tent repairing it by lamplight, driving a steel pin from a crate hinge through the break and sealing it with wax tape. The sight, bent nearly 12 degrees off-center, was flattened against a mess tin and hammered straight with the butt of his knife. By sunrise, he reassembled the weapon and wiped it clean with a strip of burlap. There were no replacement parts. The barrel was scarred. The bolt lug showed pitting from dust and grit. Still, the action held. Field records from the 36th Division Ordnance Section confirm that rifle, serial number 3057841, was logged as returned to service the next morning. At 9:45 hours, the observation team reached the ridge overlooking Monte Castellone. Enemy fire could be heard faintly from the valley floor, scattered machine gun bursts echoing against the stone. Whitman rested his repaired Springfield on a low parapet of broken rock. Through his scope, a thin shimmer of light reflected from a German position hidden in the ruins across the valley. He adjusted windage by instinct, counting the seconds between gusts, and fired 2 test rounds. Both struck the same section of dust and mortar within 4 inches. He made no further correction. A final shot followed. The sound rolled across the valley and was gone. The flash from the German scope vanished at once. Measured later by survey maps, the distance was 742 meters, a range far beyond standard field marksmanship expectations. For comparison, U.S. Army records list the average confirmed sniper engagement in Italy at less than 400 meters. Whitman's was nearly double. The rifle was turned in for inspection 5 days later at the Ordnance Depot near Venafro. Technicians recorded an unusual pattern. The bent rear sight, realigned by Whitman's improvised pin, created a fixed compensation that offset barrel vibration at long range. The fracture in the stock reduced recoil impulse by distributing stress unevenly, a structural flaw that happened to stabilize the muzzle during sustained fire. The combined defects produced a rare precision not achievable in the factory configuration. In official note signed February 15, 1944, engineers wrote that the weapon demonstrated a measurable increase in grouping consistency beyond 600 meters. They could not explain why. The rifle was retained for further testing. Its results were never replicated under controlled conditions, and the weapon's subsequent record disappears from inventory after April. Nothing remains of Whitman's name in division commendations or casualty lists. Only a single notation survives in faded ink, accuracy anomaly noted. Retain for analysis. By dusk, the valley had fallen silent. The farmhouse was marked on maps as Sector D4, its walls reduced to low shadows under the pale winter sun. The broken rifle rested across a crate of ammunition, its taped wrist holding firm, ready for another day. By March 1944, the rifle labeled 3057841 reached the Divisional Ordnance Section near Naples. The weapon arrived in a wooden crate marked Experimental, Accuracy Variation. The stock was still bound with field tape, darkened by oil and sweat. The bent sight leaf, flattened and repined, showed a clean hammer impression across its hinge. A paper tag wired to the trigger guard bore the name PFCH Whitman, though no personnel file attached. In the workshop, 2 technicians from the Army's Small Arms Repair Branch examined the damage. Both noted that the fracture at the wrist had not widened despite repeated firing. The steel pin inserted through the grain acted as a crude tension brace. When the weapon was clamped in a test vise and fired at a 200-yard target, the groupings held within 2 inches, unusually tight for a field-repaired Springfield. A second test at 500 yards produced a consistent offset to the right, roughly 8 inches at that distance. The pattern was stable. Major Leland Carter, head of the Ordnance Test Team, filed a typed memorandum. Though the rear sight leaf remains visibly distorted, the cumulative deviation results in a corrected impact point aligned with the barrel's vibrational bias. Further alteration may reduce this beneficial error. His remark was underlined twice. Film reels recovered from the depot show the testing ground outside Naples, a flat stretch of limestone with improvised targets mounted on fuel drums. Technicians in wool uniforms record impact points with calipers. Each shot cycle is measured by stopwatch, temperature, and humidity logged at every interval. The weapon is fired in single-shot configuration. Recoil is recorded using a tethered plate gauge. After 37 rounds, the barrel remains within operating tolerance. By the 5th trial, the rifle continues to print groupings smaller than any other unmodified sample. Engineers begin to suspect structural resonance rather than luck. The fracture in the stock, when reinforced by the steel pin, allows minute flexing along the wrist. That flexing, measured later with strain gauges, absorbs part of the recoil impulse that normally shifts the rifle's point of impact. The damaged rear sight, bent slightly forward, compensates by aligning the bullet's trajectory a fraction lower, countering the muzzle rise. According to the test report compiled in April 1944, the combination of structural distortion and misaligned sight leaf produces a harmonic correction effect at extended range. The result is improbable but repeatable. One line in the margin reads simply, "Accidental improvement noted." No further modification was recommended for mass production. The finding was too irregular, too dependent on the unique geometry of the damaged stock. Yet the observation drew attention from the Marksmanship training unit at Fort Benning. 2 instructors there received copies of the report and conducted small-scale experiments using shimmed and tension pin stocks. Their conclusion, dated June 1944, confirmed a measurable improvement in first-shot consistency among rifles with slight controlled flexure. For the men who tested the weapon, the implications were practical rather than theoretical. It suggested that the rigidity prized in standard rifle design might not always yield stability under combat conditions. A degree of compliant movement could absorb vibration and steady aim. The Whitman anomaly, as one engineer jokingly labeled it, entered ordnance folklore as an example of field ingenuity overriding design orthodoxy. By midsummer, the rifle itself disappeared into storage. Its final notation, transferred to ballistic section, Aberdeen Proving Ground, is the last recorded entry. Whether Whitman remained in service or was reassigned is unclear. Personnel rosters from the 36th Infantry Division list several privates with similar initials, none confirmed. In subsequent months, Ordnance reports cite new stock reinforcement procedures tested for sniper-grade Springfields, including flexible bedding materials and pin tension inserts. The language of those reports mirrors Carter's memorandum almost word for word. What began as a field repair on a cold February night had, without formal recognition, influenced the next generation of rifle stabilization methods. The file was closed in September 1944. No commendation, no follow-up photograph, only a stamped note across the folder's cover, reference retained for technical review. By 1946, U.S. Army Ordnance researchers at Aberdeen Proving Ground began cataloging anomalies discovered during the war. Among hundreds of pages detailing mechanical wear, tolerance drift, and barrel harmonics, a short entry appeared under Section 12, Field Modified M1903 Springfield, Serial 3057841. Accuracy pattern retained under structural deformation. No author was named. The weapon itself was still present in storage. Laboratory notes describe its stock repaired with an improvised pin and tape residue hardened into the grain. The sight leaf retained a shallow hammer indentation that angled it slightly forward. To the engineers assigned, the case represented an unresolved phenomenon, a malfunction that improved performance. They set out to quantify it. Tests conducted at 100, 300, and 700 yards used controlled hand-loaded cartridges, each weighed within half a grain. Chronographs recorded velocity deviation no greater than 15 feet per second, statistically normal. Yet the dispersion pattern remained remarkably small. A metallurgical report noted that microscopic flexing in the fractured wrist absorbed vibration in the same frequency band produced by barrel whip. In mechanical terms, the damage acted as a shock absorber. The warped sight, rebent to level, introduced an offset that aligned the muzzle's recovery path to target center. Captain Raymond Holt, chief engineer of the Ballistics Division, summarized the finding: subject weapon exhibits harmonic stabilization through composite structural failure. Predictability unintentional but evident. His report, later declassified, included comparative trials with unmodified rifles. Each factor a standard specimen showed minor vertical drift after sustained fire. The repaired sample did not. The difference, though small, suggested a design variable previously unaccounted for, controlled compliance. In the following months, Holt's team conducted a dozen experiments using flexible bedding compounds, pin braces, and thin rubber inserts between stock and receiver. Their aim was to replicate the Whitman effect without compromising durability. Statistical summaries show that 5 of the 12 prototypes achieved measurable improvements in grouping accuracy beyond 600 yards. The improvement ranged from 6 to 14%. No single configuration reproduced the exact stability of Rifle 3057841, but the concept had been proven. Rigidity was not absolute precision. Data from these experiments circulated quietly within post-war weapons design circles. When the U.S. Marine Corps began testing new sniper platforms in 1947, one technical note recommended compliance tolerance of 0.003 inch between bedding and receiver. The phrasing matched Holt's memorandum word for word. Years later, this principle reappeared in the M40 rifle program, flexible bedding designed to manage harmonic resonance rather than resist it. The lineage traces back, line by line, to the anomalous Springfield from Italy. The name Whitman did not appear in any of the technical publications. Only the rifle's serial number survived in tabulated data, buried among hundreds of post-war test summaries. By the 1950s, when ballistic vibration modeling advanced through high-speed photography, the idea of harmonic compensation became an accepted engineering parameter. A margin note in one report, unsigned, reads simply, possibly first observed in field conditions, Italy, 1944. Modern ordnance historians reviewing the Aberdeen archive note that this single weapon forced a subtle shift in small arms design philosophy. Prior to 1944, standard doctrine treated the rifle as a rigid instrument, stability defined by hardness and immobility. Afterward, designers recognized the possibility that slight structural give could enhance repeatability under recoil. The phenomenon entered textbooks decades later as dynamic bedding response. The physical rifle itself was decommissioned and stripped for analysis sometime before 1951. Its stock was sectioned into cross samples, the steel pin recovered and catalogued under Artifact Code A2728. The report's final page lists no conclusion, only a simple directive: retain results. Do not replicate without field verification. In the end, a single field repair in a ruined farmhouse became an unacknowledged data point that reshaped long-range marksmanship. There was no ceremony, no photograph, no citation. Just a broken rifle that, by accident and persistence, recorded what factory tolerances could not. By the early 1950s, the Springfield rifle had already vanished from frontline service. Semi-automatic Garans and new bolt-action sniper models replaced it across Europe and Korea. Yet among ordnance officers and small arms instructors, the name Whitman rifle remained a quiet reference, a shorthand for accidental precision born of necessity. No official record tied the term to any single man. It appeared only in marginal notes and oral recollections, a broken stock that shot straight. At Aberdeen, the technicians who had handled serial 305-7841 retired or transferred. Their reports gathered dust in climate-controlled cabinets marked defect studies, World War II. When the archive was surveyed in 1957, the file was listed as low priority, retained for historical interest. None of its data were ever applied to new production, but its conclusions quietly persisted through informal engineering habits, subtle allowances for vibration, attention to recoil harmonics, and tolerance for minute stock flexure. These traces shaped the next generation of precision rifles without anyone remembering their origin. In interviews decades later, retired marksmen from the 36th Division recalled no one named Whitman. Field rosters were incomplete, casualty lists had been merged during postwar reorganization. Some remembered a corporal who repaired his weapon with packing wire. Others spoke of a marksman who once struck an enemy observer at impossible range near Casino. Their stories overlapped, fragmentary, always ending with the same line, "He fixed his rifle, and it worked." Ordnance historians reviewing the technical documents note the absence of personal acknowledgement. Every report speaks only of mechanical behavior, data sets, and measurements. The human decision that produced it, a man sitting under a lantern, aligning cracked wood and bent steel, is missing from the record. What remains is the engineering artifact, the proof that imperfection can, under pressure, create its own precision. In 1961, when the Army introduced the M40 sniper rifle with its newly formulated epoxy bedding system, a single reference line in the design notes mentioned compliant bedding verified by historic test, Italy. No further detail followed. The M40 became a benchmark weapon, its accuracy praised for decades. Its theoretical ancestor, the field-repaired Springfield, remained unidentified. By the late 20th century, the idea of structural resonance control was fully integrated into small arms design. What had once been a battlefield improvisation evolved into a controlled engineering science. Yet the chain of influence, from a damaged rifle in the Apennines to laboratory standards in Maryland, survived only as a technical curiosity known to a handful of researchers. The official archives of the U.S. Army Marksmanship Unit preserve a single photograph labeled Unknown Springfield, Field Repair, Italy, 1944. The tape on the wrist has darkened to near black. The rear sight leans forward a fraction of a degree. A faint tag hangs from the trigger guard. The rest of the image is unremarkable, just another rifle laid on a workbench, its imperfections recorded and forgotten. Across 70 years of ordnance evolution, its legacy exists only in calibration charts and training manuals. Each modern sniper rifle carries within it a trace of that accident, a small allowance for movement, a calculated forgiveness written into steel and wood. The story behind it, like so many in wartime engineering, belongs to no one. The war ended. The documents were filed. And in a quiet room of the Aberdeen archive, the test folder still bears the same note in fading type, subject weapon, M1903 Springfield, serial 305-7841, accuracy anomaly confirmed. Retain for reference. In the years that followed, small deviations like the one recorded in Rifle 305-7841 became central to how ordnance engineers defined accuracy. What began as a battlefield improvisation transformed into a philosophy. Precision was not the absence of error, but the management of it. During the 1960s, as new sniper platforms emerged from Remington and Winchester, engineers applied flexible mounting and harmonic tuning not as improvisations but as design principles. The reasoning traced, though seldom credited, to a wartime anomaly first measured in an Italian valley. Declassified correspondence between the Ballistics Division and the U.S. Army Infantry Board mentions the case indirectly. One note from Captain Holt reads, "Revisit field anomalies noted Italy 44. Field conditions produce valuable deviations." The phrase, understated and bureaucratic, acknowledged what the statistics alone could not, that necessity, not theory, had expanded the limits of precision. By the 1970s, as Vietnam-era sniper programs revived long-range training, ordnance schools taught a module on barrel harmonics and stock flexure. The origin was never named. Yet instructors at Fort Benning recalled a story passed quietly between courses of a soldier who refused to surrender a broken weapon and found, by persistence, a better way to aim. Whether that story referred to Whitman or to a composite of similar men no one could say. The data existed, the man did not. In 1982, a curator at the U.S. Army Ordnance Museum compiled a reference list for unique test weapons. Among them appeared Springfield, M1903, damaged stock, improved grouping. Its serial number matched 305-7841. The artifact was believed to have been scrapped during a storage consolidation, but its record remained in the museum ledger. The entry carried no comment beyond origin unknown. The curator, in a later interview, described the moment he first noticed it. There was something poetic about it, a rifle that shot straighter because it was broken. His statement was not sentimental. It reflected a professional respect for the strange logic of field innovation, the unplanned discoveries that emerge only in war, when regulation and survival meet in compromise. Archival sound recordings from that period include test officers discussing the rifle's grouping patterns. Their tone is dry, procedural, precise. Yet beneath the analysis lies a quiet recognition that human improvisation often outpaces design. That Whitman rifle, if the name was ever used officially, symbolized this tension. It represented the line between craftsmanship and chance, between a soldier's instinct and the engineer's drawing board. Modern ordnance specialists studying historical ballistics recognize the case as an early instance of adaptive engineering, where a defect becomes a functional parameter. The principle remains relevant in contemporary weapons research, from carbon fiber stock tuning to vibration-dampened optics. Each iteration carries, unknowingly, a trace of that single data point from 1944. The legacy of the weapon endures not as a myth or moral but as an equation. A broken stock changed how rifles were built. A misaligned sight refined how accuracy was measured. And somewhere in the space between failure and precision, an unrecorded soldier altered the mathematics of marksmanship without ever knowing it. As the documentary closes on the archival photograph, a weathered Springfield resting on a workbench, light falling across the taped wrist, the voice of the narrator would fade to silence after one last calm sentence. Innovation is often recorded in blueprints, but sometimes it is written in fracture lines and field tape. By 1994, the Army's ballistics archive underwent digitization. Thousands of ordnance reports, including those marked minor defect studies, were scanned and indexed for internal research. Among them, the file labeled Springfield, serial 305-7841 reappeared for the first time in half a century. The type pages were brittle, their edges yellowed with age. Attached to the first sheet was a small black and white photograph, the rifle laid on a bench, the crack in the wrist clearly visible, the sight leaf still leaning forward. The tag read only, ACC the anomaly, Italy, 1944. Technicians performing the scan noted the irregular data, test distances, grouping diameters, vibration readings. Most entries were mechanical. None mentioned a name. The program that indexed the files classified it under prototype precision data. For all digital purposes, the rifle that began as a damaged field weapon was now stored beside experimental long-range prototypes. Its story, stripped of human detail, had become an engineering precedent. In 2001, a ballistics researcher at Quantico cross-referenced the file while studying resonance behavior in modern sniper platforms. The variables, harmonic oscillation frequency, stock compliance, barrel whip amplitude, all matched models used in the M40 and M24 rifles. When asked during a training symposium where the earliest data originated, the researcher replied, Italy, sometime in '44. We don't have the name, only the rifle. That quiet admission reflected the entire arc of wartime innovation. Most inventions born in the field carried no signatures. A broken hinge became a stabilizer. A misaligned sight became a correction tool. Each was absorbed, improved, and standardized until its origin dissolved into the machinery of progress. Visitors to the Aberdeen Proving Ground Museum today can still see a small brass plate mounted without context in the small arms section. It reads simply, M1903 Springfield, Structural Modification Test, 1944, Donor Anonymous. No serial number, no service unit. Only a faint trace of oil on the wood beneath the glass. Every generation of riflemen since has benefited from lessons distilled from such accidents, from men who refused to discard damaged tools, who saw function where others saw failure. Their influence persists not in medals or citations but in the subtleties of design, the curve of a trigger guard, the resilience of a stock, the way a rifle settles after each shot. In the end, the broken rifle became more than a weapon. It became evidence of a pattern repeated throughout the war, that innovation often emerged not from laboratories or design bureaus, but from cold hands in the mud, from soldiers solving immediate problems with what they had. These small acts, uncelebrated and unrecorded, shaped the technology that defined the modern battlefield. When the documentary fades to its final image, the cracked wood, the faded tag, the quiet hum of archival lights, the narration ends with a single, measured line. History remembers the designs that succeeded. Engineering remembers the ones that broke first.